Simulating the level of natural complexity seen in this spinning molecule represents a hard mathematical wall for traditional computing. For decades, progress relied on shrinking microchips and speeding up the billions of deterministic bits that define our current machines. However, increasing the speed of a standard processor fails to solve the problem of exponentially growing variables. Overcoming that limitation requires a move toward an architecture built on the probabilistic rules of quantum mechanics. Solving the universe's most intricate codes requires a machine that processes information through the same physical laws nature follows. That shift starts at the absolute base level, with the qubit. This diagram illustrates the distinction. The classical bit on the left acts as a rigid switch, locked to a value of 0 or 1. The qubit on the right exists in a superposition, a fluid, overlapping combination of 0 and 1 at the same time. This pulsing map shows the qubit's spectrum of probability. Defined by complex numbers, it remains as pure mathematical potential until the moment of observation. Utilizing these probabilities gives the system a unique capacity to navigate near-infinite landscapes of potential answers. Entanglement allows two qubits to link so that the state of one instantly dictates the state of the other, regardless of physical distance. Locking the left node here forces the right node to react immediately. Interference organizes entangled states into useful data. Here, multiple sine waves at different frequencies represent diverging paths of a calculation. When overlapping, algorithms force incorrect out-of-phase probabilities to cancel out, while correct in-phase waves reinforce into a single clear peak. Pairing the connection of entanglement with the filtering of interference allows the system to evaluate massive, complex matrices of data simultaneously. Engineers control this process using reversible logic gates, like the Hadamard gate, to construct a functional quantum circuit. These circuits run specialized quantum algorithms. Shor's algorithm, for example, focuses specifically on factoring massive numbers. This visualization shows a 50-digit number fracturing into its prime components almost instantly, bypassing the sluggish linear calculation path below it. Since this math is the bedrock of modern RSA encryption, a powerful enough quantum machine would compromise current security standards. When a machine solves a problem that is functionally impossible for a classical computer to finish, it reaches the threshold of quantum supremacy. Reaching that milestone transforms quantum computing from a theoretical experiment into an urgent global security priority. Extracting answers comes with a severe cost. Measuring a quantum circuit causes wave function collapse, instantly destroying the delicate quantum information the system holds. This fragility creates decoherence, the primary physical obstacle to wide-scale adoption. The slightest interaction with the environment, stray heat, microscopic vibrations, or faint electromagnetic fields, forces the qubit to lose its probabilistic state and scrambles the calculation. The sensitivity to probability that gives a quantum computer its power is the same trait that makes it difficult to physically engineer. Fighting decoherence requires extreme isolation. This dilution refrigerator houses superconducting circuits, cooling them to near absolute zero to maintain stability. Even with these measures, we are currently in the NISQ era, noisy intermediate-scale quantum. These machines are expensive, prone to errors, and limited to low qubit counts. To produce stable results, they must work in hybrid networks alongside traditional computers. Because of physical constraints, quantum systems are ill-suited for basic tasks, personal devices, or web apps. The investment targets specific fields: molecular drug discovery, specialized data cryptography, and advanced material science. Quantum computers function as specialized instruments, engineered to speak the universe's native language and simulate the probabilistic behavior of nature.